Well, now we are in Module 9 and this is the last lesson of Module 9, Lecture 4. It is an introduction to zero-knowledge proofs. So, let's see. We are going to see an introduction to zero-knowledge proofs, the different concepts that are behind this primitive, and finally we will briefly discuss one of let's say one of the first systems to prove something with a zero-knowledge proof, which is SNOR, the SNOR identification system. Okay, so the idea here is that you finally know how know the basics, the outcome of this this lesson is that you know the basics of zero knowledge, that you have some intuitions, and also some knowledge about the basic SNOR identification protocol. And obviously also we are going to discuss a little bit the application of zero-knowledge proofs to blockchain systems and why they are important and useful. So, so let's go with an introduction to zero-knowledge proofs, and maybe we can start with some questions. For example, I mean, what is a zero-knowledge proof? Is something that we would like to know. Even what is zero knowledge? I mean, what does zero knowledge mean? And obviously, what does it mean to prove something with zero knowledge? I mean, it seems like counterintuitive. I mean, I'm proving something without knowledge, or what do we mean exactly? Okay. Well, there is a relationship, by the way, between digital signatures, for example, and some zero-knowledge proofs. We would like to discuss also, as I said, applications of zero-knowledge, and in particular, which applications of zero-knowledge are specifically interesting for blockchain systems. So let's start with some of the origins of the term zero-knowledge. And well, these systems were proposed in the 80s by a couple of MIT researchers, well, 3 MIT researchers, which are Safi Golbasser, Silvio Micali, and Charles Rakoff. And they were working on problems related with interactive proof systems. I mean, they were studying systems in which there is a prover and a verifier, and the prover and the verifier are interacting to finally prove something. The main contribution of this work, it was like changing the point of view, because I mean, we have a prover and a verifier, okay. And the prover is well, they're interacting, and the prover is proving something to the verifier. If I ask here in this scheme, which is the entity that you trust, probably all of you will answer the verifier. I mean, who is trusted? The verifier. The verifier is trusted, and the prover, the prover is potentially malicious. I mean, the prover is trying to prove something. I mean, maybe he's trying to cheat us and try to prove something that is false or fake. Okay, so in general, verifiers were trusted parties. Well, while provers, well, they need to prove. I mean, they need to provide proofs to verifiers. Okay. So, but Golbasser, Micali, and Rakoff, they started to think, okay, and what if we consider that the verifier is not so trusted? Okay, what if the verifier is also considered in some way a malicious party or potentially malicious party. Okay, and I mean, the question was, should we always trust the verifier? Well, instead of only worrying about the prover and the honesty of the prover, they started to also question the honesty of the verifier and say, okay, what happens if in any scenario we would like to introduce some distrust in the verifier? Okay, so what do we happen? What happens if we don't trust the verifier? And the specific concern that was raised at this moment was about information leakage. I mean, how much information do I need to leak or to provide to the verifier to check something? And well, this is the main question around zero knowledge proofs, okay, or ZKPs. The idea is how much extra information. I mean, the verifier. I mean, I need to, as a prover, I need to prove something to the verifier, and this is the general setting. So yeah, we need to do this. We're going to interact, and the prover is going to prove something to the verifier. But the idea here is, okay, but how much extra information? Extra means, I mean, you are going to learn that the statement or the statement, the thing that I'm proving is correct. Okay, as a verifier, this is okay. But I don't want you to learn anymore and anything else. And this is why the word, the definition, zero knowledge. Beyond this proof, I don't want to learn you anything. Okay, the prover doesn't want that the verifier learns anything beyond the fact that the statement that is proving is true. Okay, and this is why it appears this concept of zero knowledge. So, providing more a definition of zero knowledge, a zero knowledge proof is a protocol. I mean, it's an exchange of messages. Okay, so it is a protocol between two parties. One prover, sometimes we call Peggy to the prover, and Victor to the verifier, or well, I can say prover verifier or Peggy Victor, whatever is equivalent. Well, there is a zero knowledge protocol. Is a protocol between two parties, a prover and a verifier, and in which the prover makes some statement and tries to convince the verifier that this statement is true. And for doing so, there will be an exchange of messages, but this exchange of messages will reveal nothing else than the statement that I'm proving is true. This is the idea. And yeah, for example, let's see how to prove. Let's see how to build a proof for some statement, and then see if we are doing it in zero knowledge or not. And for example, consider that we have a card. Okay, we pick a card from a poker deck. Okay, and in a poker deck we have we have 4 different so let's see the example better. Okay, so we have a deck of poker, and there we have we pick a card. For example, let's say we pick the ace, which is a red, and then the idea is that you pick a card and you want to prove me that the color of this card. Okay, remember that we have diamonds, I mean, clubs and spaces are black, while diamonds and hearts are red. Okay, so you pick a card of the deck, and you want to prove me that this card is red. Okay, but do you want? And this is the statement that I want to prove. Okay, well let me be the prover. Okay, I'm the prover, and I want to prove you are going to be the verifier. I'm going to prove you that I pick a card that is red. Okay, this is the statement. Okay, so this is very important in zero knowledge proof. It's just define the statement. And in this case, the statement is I picked a red card. Okay, but I don't want you to. Okay, so how can I prove you that I pick a red card? Okay, one option is to show you I can show you the card. Okay, but the problem there is this is not zero knowledge, because I'm not only learning that the card is red, maybe I'm learning that the card is also is one from the hertz, and also the number. In this case, that this is not that it is the as. Okay, so is the A. So how can I? This is not a good way then of. I mean, this is not a zero knowledge way of proving that a card is red. Okay, so how can we do it in zero knowledge? Well, I can give you the deck with all the cards and show you, for example, all the black cards. If I show you, I mean, we have 13 cards per space, so if I show you 26 black cards, it means that all the black cards are in the deck. So the card that I have must be red. Okay, so and I'm proving in this way. Yes, I'm proving this with zero knowledge. Okay, so now let's see examples of zero knowledge in the context of computer security. Still, this is not for blockchain, but yeah, in general for computer security. So imagine that you want to log into a server and you want to use a secret password. Okay, so typically what happens in the internet, in the servers of the internet, you provide the user and password. Okay, you provide a user and a password, and then the server essentially checks that the password is okay. No? To be more precise, typically servers just store the hash of the password, and then when you provide the password, they hash the password and check that the store version is the same. Okay, but anyway, you need to provide the password. Okay, so this login process, in fact, can be viewed as a proving system, because you're proving that you know the password, but you're providing the password. So it is not zero knowledge in this case. So it is like the example of the cards before. So I would like to, zero knowledge systems can be used, for example, for this purpose. I mean, I will, in fact, you still are going to store a hash of my password, and then I'm going to provide you a proof, okay, that I have a password that when hashed gives this value, okay, the value that you have on your disk, which is the hash of the password. Okay, so I'm going to, the idea here is to prove you that I know the preimage of a hash. In this case, this is the statement. I know that the preimage of this hash, I know the preimage of this hash, and you're going to be convinced. Okay, and I'm not going to tell you anything else. In particular, I'm not going to show you the password. Okay. So this is one use of zero knowledge for general computer security, and talking about and then let's see some properties that we need to fulfill, that zero knowledge need to fulfill. We need, in general, these systems need to fulfill three properties. First, completeness. I mean, completeness means that the protocol, it is possible to run the protocol. I mean, an honest verifier can run the protocol, and an honest verifier runs the protocol and convinces the verifier. Okay, so this is what we say completeness. Soundness means it is usually the hardest to prove. The soundness means that the prover cannot convince the verifier that a statement is true without being true. Okay, so this is the soundness, and this is the hardest, because I mean the soundness means that the prover cannot cheat. Okay, well, these are like the two classical properties, and now we are adding a new one, which is zero knowledge. That is, the verifier learns no information beyond the fact that the statement is true during this process of proving, creating the proof. Okay, so let's build another example. Still is not it is an intuitive example, okay, and it is very typical, by the way. It is the Alibaba cave, and in this case, the scenario is the following. There is a cave here. There is the verifier. There is a verifier and a prover, as always. And, the cave has here a door, and the prover wants to prove to Victor that that she knows a secret word that that can open this door here. Okay, then there is a secret word that opens this door. Okay, and I want to prove you that I know the secret word. I want to convince you, but I don't want the prover wants to keep this secret word secret. I mean, only known by her. Okay, so, and how do we prove this with zero knowledge? Well, then the verifier, the prover and the verifier start both here. Okay, here we have the, well, let me draw the verifier and the prover, and then the prover enters the cave and decides where to go, up or down. Okay, and maybe goes up. Okay, but the verifier is not seeing anything here. He's outside the cave. Okay, and then the verifier enters the cave. Okay, and says, okay, you have to go up. I mean, you have to come through the upper branch, through A, let's say. Okay, and no, imagine that the prover just decided to go this way, the B way. Okay, so it is outside it is in the other side of the door. So now he needs to use the secret word to open the door and finally go outside to go as asked by the verifier. Okay, so in this case, the prover needs to use the secret word to fulfill the request of the verifier. Okay. the idea is, okay, but as a verifier, that I tell the prover to go, to come to me through A, and I see the when I see the verifier coming through A, this is enough to be convinced that he knows the secret word. And the answer is no, because the verifier could be lucky and could have decided to go up. Could decide to go through A, and then when I ask come back through A, okay, well, she doesn't need to use the secret word, okay, to go outside. So with 50% of the possibilities, the verifier needs to use the secret key. With the other 50, doesn't need to use the other key. Okay, so I need to be more convinced. This means that my soundness which is this idea of a malicious prover making me think that that the statement is true. In this case, the statement is I know the secret key I know the secret word that opens this door. The soundness is just 1/2 here, okay? With 50% of the possibilities, the verifier is going to cheat me because she doesn't know the secret word, but she is lucky, and then he is coming through the correct path. So the idea to increase the soundness is just repeat. And then they go back again and repeat this and repeat and repeat and repeat and repeat. And each time we repeat, the probability, if we repeat this n times, the probability that without having the key, the verifier guesses all the time is as close to 0 as we want. Okay. And as you see here, the soundness is expressed as a probability of accepting that a statement is true when it is not. Okay. So now we can define in a more precise way the 3 properties, okay, which are completeness, sound, and soundness. to start, okay, completeness means that an honest verifier can create a valid proof and convince an honest prover can convince an honest verifier. It means that it means that there is a protocol that can be run, okay, and both parties are honest, okay. The soundness means that a dishonest prover cannot generate a valid proof. Okay, this is why in the previous example we need to repeat to achieve soundness. Okay, in the previous scheme, in the previous example of the Alibaba cave, the completeness is like the description of the setting. I have a cave. You can go up, you can go down. You can do anything. When the system is complete, it means you can generate the proof. Okay, and when the system is sound, it means okay, you can not only generate the proofs, but you cannot generate incorrect or invalid or dishonest proofs. Okay. And what about zero knowledge? In zero knowledge, when using zero knowledge means that the verifier learns nothing beyond the truth of the statement. And this property is specifically designed to protect the prover, because the prover doesn't want to reveal any extra information. So how can we prove something that is the problem is okay, and how I'm sure that something is zero knowledge, or how can I prove something with zero knowledge? Well, the trick is to generate is to define a simulator. The concept of simulator is the concept that allows us to create a definition that we can work with for zero knowledge. And the simulator is a special verifier. Okay, is just a special verifier, and let's see what let's see what's a simulator in the case of the Alibaba. Okay. So the idea is that the verifier, as I said, the simulator is a special verifier. Okay, and then let's consider that the simulator is this guy here. And this guy has a camera here. Okay, and the simulator is another entity. Is always with the verifier. So the simulator is as I said, is a special verifier. It's an entity always with a verifier, and it is going to record everything. Okay, it is going to record when the prover goes up, goes down, and when goes out, and so on. Okay, so yeah, and then we will have a record of everything that has happened. Okay, and now the idea is that, okay, why this is zero knowledge? Because this record doesn't tell us anything about, I mean, seeing this record, I mean, again, the simulator is going to record everything, okay, and we are going to have a recording of everything, and the question is, this recording is proving that the prover has the secret word. I mean, with this recording, we can prove that the prover has the secret word. Okay, and the answer is no. I mean, for example, you can go to a judge and say, okay, this prover has the secret word because I don't know. There is someone stole something. Okay, it must be this guy here, because he knows the secret word, because here I have the recording that proves this. Okay, but this is not true, because this recording is not proving anything, because I mean, the prover can always say, hey, I don't have the secret word. Okay, I just I agree with the verifier all the movements. Okay, we knew that he was going to say A, B, B, A, and I just follow this pattern. Okay, I just follow the pattern that we previously agreed. Okay, so this is what we say a simulation. It means that all this interaction can be simulated. If this interaction can be simulated, it means that from this interaction you cannot learn anything. Okay, this is the idea. Okay, well, these are like general concepts of zero knowledge systems. Well, here's some more technical stuff. Maybe we can just mention it. All the properties, I mean, the completeness, the soundness, and the zero knowledge, all of them can be fulfilled in different ways, let's say. They can be perfectly fulfilled, they can be statistically fulfilled, and they can be computationally fulfilled. Okay, when something is perfect, it means that this property is guaranteed or is always true with probability 1. Okay, so the probability of not fulfilling the property is 0. In other words, for example, the example with the red car is perfectly sound. Okay, when something is always fulfilled with some property, when some property is fulfilled always with probability 1, we say that this property is perfect. Okay, for example, as I said, in our example of the playing with the red cards, our proof was perfectly sound. Is the probability that you cheat me is 0. I mean, if I go to the deck and I see 26 black cards with probability 1, the one that you have on your hands is red. Okay, so this is perfect. We can have also statistical fulfillment of our probabilities. So this is when, well, there is a probability, finally. I mean, in the Alibaba cave, for example, the soundness, okay, the probability that you cheat me, soundness, the soundness is statistical. I mean, it has a certain probability, okay? Usually we get some bound by some repetition. I mean, in our example, we get some bound by repetition. I mean, if we repeat 4 times, then the probability that you cheat me is 1 half, 1 half, and 1 half. Okay, so it's 1/16. Okay, and this is the probability. And there is also another notion for fulfilling these properties, which is called computational. Well, this is more technical, but let's say that this is when one of the properties is fulfilled with, but considering that the, for example, soundness. Okay, this is the probability of the prover cheating. Well, in the computational model, the prover is assumed to have a limited amount of resources, not infinitely many. I mean, it has a computer and cannot do. I mean, can do some computations, but cannot. For example, cannot reverse a hash function, for example, something like that. Okay, when you consider that your adversary is computationally bounded, then we say that the property is fulfilled in a computational way. Well, this is rather to be more precise with the definitions, but I think, well, with the previous definition is more or less okay. Well, so yeah, essentially, when we talk about proofs, in general, there are many different types of proofs. I mean, there are legal proofs, they are from authorities, they are scientific proofs, philosophical, mathematical, okay? But in this case, we are talking about this new area, in this new space. Proofs are a process that need interaction and probability. Okay, there is an interaction between two parties, and there is a probability that that the proof is okay, that is sound, that is zero knowledge, and so on. Okay, so okay, so Still there is some, according to the type of properties that you are fulfilling, we also have different types of zero knowledge of zero knowledge the zero knowledge property we have different types of zero knowledge properties. Okay, let's see which are these. Zero knowledge proofs. These are statements about some fact, and each statement is something. Let's say something in some. I mean, I'm proving something that is true. Okay, this is a zero knowledge proof in general. So, for example, in our example, there is some secret that opens this magic door in the cave, for example. Okay, or that n is a set of some composite numbers. So whatever, this is a proof about something that is true or not true in general. Okay. Then we have proofs of knowledge. I mean, here is I'm not proving something that is inherently true, but I'm proving that I have something on. I have something on my hands. Okay, these are statements about my personal knowledge, not about, let's say, universal knowledge, but about my personal knowledge. This is beyond the fact that something is true or not. It is about if I know that, if about what the prover knows. Okay, and we call this proof of knowledge. Okay, for example, I know a secret word that opens the magic door in this cave. Okay, so, well, in general, we are interested in this other type. Okay, in general, in zero knowledge, we are interested in proofs of knowledge. Okay, because we want proofs. We want to get proofs from the prover that he knows something. Okay, these are the most interesting. And then this just are some more specific definition, which are arguments of knowledge. Well, it means that it is a proof of knowledge again, but the soundness, I mean, that you cannot be cheat is a matter is because the prover is computationally bound. I mean, it doesn't have infinitely many resources. Okay, and then in this particular case, we call it argument of knowledge. Okay, and in fact, for blockchain, these are the most used ones. So, okay, let's present some examples of zero knowledge for blockchain. For example, I mean, there are two main applications of zero knowledge in blockchain. One is privacy. I mean, public blockchains, mainly in public blockchains. In a public blockchain, all the nodes, all the nodes in the blockchain, and all the information that goes, all the transactions that go through the network, they're transparent. I mean, they each time I send a transaction to the network, this transaction is seen by everybody. Okay, so we have this transparency. But the problem is that if we want to use this technology in a corporate or in an enterprise world, companies they don't want their data to be seen by everybody. Okay, so but we need to process data also. So I mean, you may think, okay, then let's send encrypted data here. But this is also a problem because, I mean, yeah, we want to process data, okay, and process these transactions. We want to do some processing in the transaction. So the idea is, how can I process something? How can I process a transaction, for example, and well, be sure that some facts, some statements about the transaction, but without seeing other information. To put it in a more concrete example, one of the examples is how to create private transactions on a public blockchain. And this is the example of Zcash. So I send a transaction to the network and with some parameters, and then I send a proof. Usually proofs are denoted with the Greek word pi, and essentially this proof states that the transaction is correct. I mean, the sending address has enough funds, is made by the correct owner. I mean, the owner of the associated private key, and well, is transferred to someone else, and so on. I mean, everything is correct, but you're not going to see who is sending the transaction, to whom, or the amount. Okay, only a proof that the transaction is well done, but not exactly from where it goes to where it goes, or which is the amount of transferred cryptocurrency. Okay, so yeah, there are a lot of applications that involve privacy. I mean, it means that you see transactions on the blockchain, and these transactions carry proofs, and these prove some facts. Okay, but you don't see other facts. For example, in this case, who is sending the transaction? For example, this is going to be hide. This, after this slide, is when you should realize that zero knowledge proofs are really a match made on heaven for blockchains, because we in our blockchain we will still have the transparency. All the infrastructure of the blockchain is shared, but we don't need to show everything on this public blockchain network. Okay, zero knowledge proofs are the technology that allow to use public networks, but keeping some parts, some inputs of the computation of the checks that we do private. Okay. For example, other uses are, for example, compliance. I mean, you can create proofs of solvency. I can prove you that I have enough funds, but without revealing to who these funds belong, or whatever. Okay, or taxes, for example. This is, I think, that this is going to be one of the main things that we need to build for blockchain. A way of paying taxes, but I mean, I want to create a transaction. This transaction, you will not know this transaction from. I mean, again, you will not know the from or the to, but I'm paying the taxes correctly, and we can use zero knowledge to prove these things, for example, and then. The other big application of zero knowledge proofs is for scalability of blockchains, and here we have a lot of layer 2s. They started with rollups, which here we are not worried about privacy, but we are worried about checking the computation. I mean, the idea here is that I send a transaction to a network with a proof, but inside this transaction I'm proving I am this proof, but say proofs. I mean, sorry, we can send here. Well, let's simplify it a little bit, but I can send a transaction to a network with a lot of information about many transactions. Okay, and then a proof of the execution of these transactions. Okay, and the idea of rollups is that we can easily verify this proof, and this proof is verifying that I maybe perform thousands of transactions, and you don't need to run the execution of your transactions on your own, or each node of the network doesn't need to repeat the execution of these transactions. They just check the proof that the computation is well done, and that's it. Okay, something like and this concept is now pushed a little bit more, and there is a lot of projects building Ethereum. In the case of Ethereum, they are building Ethereum virtual machines. I mean, they are building processors that can, with a proof, I mean, they don't need to process all the transactions. The verifiers don't need to process the transactions. They just receive a proof, and they check that the state is changed correctly, something like that. Okay, so well, maybe it's a little bit complex to explain in just a few words, but the two main areas of applications of zero knowledge in blockchain systems are privacy and scalability. And then, just to finish, the idea is to provide an example of a zero knowledge proof that is used in reality, which is a SNOR, and just to show you one practical example. Okay, well, SNOR is an interactive protocol, so it's an interactive protocol between a prover and a verifier. And the idea is that I have a prover, I have a verifier, and the idea is to create a proof. The prover wants to prove that she knows a secret value. Okay, let's call this secret value W. Okay, this is something. W is what we also call the witness. Is something known only by the prover. Okay, only known by the prover. Okay, and the prover wants to prove that he knows W, but without showing W to the verifier. In fact, what the prover is going to prove, the concrete statement, we're going to formulate it in a moment, but we're going to use one property. It's a mathematical property that if I have a number, let's say J, and I raise it to W, and I do modulo P. Okay, this is a mathematical operation, modular operation, and let me call it T. Okay, well, there is a mathematical principle here that says that you cannot get from T and knowing G and knowing P, you cannot get W. Okay, this is called the discrete logarithm problem. Okay, and essentially what we are going to prove is, okay, I know the prover and the verifier, they're going to know T. Okay, and the prover is going to prove that he knows, the prover, he's going to prove that she knows W such that G to the power of W is T. Okay, so let's go again. So if I have a number that we call G and I raise it to W and I do modulo P, you can do this operation. If you know W, I mean, G and P are parameters that we know. Okay, this is the statement. It's a little bit mathematic, this statement, but the statement says, okay, I'm going to give you a group. G is a generator of the group, but it doesn't matter too much. I just wanted to prove to, well, this is in a high level, let's say. Okay, if you take G, I'm going to prove you that I know the discrete logarithm of T. Okay, so T is also known. So if I know W, I can take G rise it to W, and then take modulo P and compute T. Okay, so, but the other way around is impossible. I mean, if I give you T, it is not possible that you compute this W, okay? Because there is a modulo operation here that makes this very difficult. In fact, is one of the problems, general problems that we consider in cryptography, which is called the discrete logarithm problem, okay? So, then I want to prove you that I know the discrete logarithm of T. That is this W here, okay? And well, Schnorr created a protocol for that that can do this without revealing W. And the idea is more or less simple, let's say. The idea is that the prover generates a random number, K, okay? Let me draw it here. Okay. You will need to in the practice, by the way, you will need to look for more information about this protocol. Okay, I'm just outlining it a little bit here. Okay, how do I prove you that I know W? Okay, so the prover wants to prove that she knows W, but without revealing W. W such that when you do G to W modulo P, this is T. Okay, T is public, but W is secret. Secret. Okay. Well, the protocol goes like that. The prover generates a random number K. Okay. And then it's like blinds this K by taking J to the K modulo P, and we're going to call this R. Okay? And then sends this value R to the verifier. The verifier generates a random number C and gives this C back to the prover, and then the prover sends this S value, which is the witness, this is secret, times C, this is the one that the verifier provides to the prover, plus K, this is also secret, only known by the prover, okay? Because the prover provides a blinded version of K, okay, G to the K, which is R. Okay, so the prover generates this equation, computes this equation and computes S and provides S to the verifier. And then the verifier essentially what needs to do is check this equation in an encrypted way, in a blinded way, and is taking J to the S equal J to the W times C times J to the K. Okay, and this is the equation that we check. S, C, and R, they are public. And here, see that G to the W, this is T. Okay, so this is the check that we do. Okay, well, the idea is, okay, you will, this is a, you are checking that you know W, but without revealing W. Okay. Again, this is a very high level overview of this protocol, and in the practice what you will need to do is to go deeper and check it in more detail. Okay, and this concludes this lesson, in which we devoted most of the time to describing the zero knowledge, the properties, the type of proofs that we have, some use cases for blockchain, and a little bit, in a high level, one system for creating a proof of knowledge of of a secret value that is called snore, and that you are going to develop more in the practices.